You'll need assignment 63 to follow along with this instruction. This lesson is intended to give you a more theoretical understanding of what are these forces that make a bond. So here we have this simple model of a covalent bond here. What you should see is that there's a force pulling this nucleus toward the electron. It's an attractive force. There's a force pulling this nucleus toward the electron. It's an attractive force. Those forces hold this together as a bond. There are, in addition to these attractive forces, there are forces of repulsion. This positively charged nucleus here repels this positively charged nucleus here. So there's also repulsion, but the repulsion is not as strong as the attraction. So attraction wins in this situation. And whenever the attraction wins, you have a bond. Here's the first scenario, simulated in interactive physics. And you can see that the attractive forces draw the nuclei to the middle, where a bond is formed. This equation is telling you that humans have figured out how to calculate forces. It is not random. It can be mathematically determined. We need to define some terms here. K is a constant. I'll misspell it so it looks like K stands for constant. Q is the charge. Charge of the first object. Q2 is the charge of the second object. D is the distance between the two objects. These have to be charged objects to have electrostatic forces. This is all that matters. K is a constant for our universe. I'll make up a very simple number for K. This is not the truth, but it's simple to do the math. We'll say the K is 4. Here I'll show you how to apply this equation in a very simple situation. We have an electron. We have 2 protons. We can calculate the forces using this equation right here. Charge, let's take a look at this and say this is Q1. And this electron will be Q2. What is the force of attraction between them? Well, that depends on the distance. Here we have a distance of 1 angstrom. We'll just call it 1 distance unit. Let's calculate the force of attraction. So the force here will be K, which we're saying is 4, times Q1, which is 1, times Q2, which is also 1. It's negative, but that just means it's attractive forces. The distance is 1. We square that. The force here is 4. I'm labeling this as 4. I'll label it now with these strange letters here. That's a small n and a capital N. That would be nanonewtons. Don't worry about the unit of measurement. We'll just keep it consistent. You should see that if we look at the second nucleus, this is exactly the same situation. Distance again is 1. Charge is +1. Charge 2 is -1. So this has to be symmetric. It has to also be 4 nanonewtons, drawing these toward the electron. However, there's also this force of repulsion out here that we can calculate. Now, for the repulsion, I'll say this is Q1 and this is Q2. See, I'm just defining which objects are interacting. I'm now ignoring this electron in the middle, ignoring it, ignoring it, ignoring it. The forces are not affected by whether there's something in the middle. That may seem counterintuitive, but it is true. So this nucleus repels this nucleus. Let's find out what the forces are. All right, so here we go. F equals K, which is 4. Q1, which is 1. Q2, which is 1. D is now 2 units, right? It's 1 plus 1 equal to 2, square 2. You should see this gives you an answer, a numerical answer of 1 units of measurement, nanonewtons. So it's symmetric, it acts on both particles. You should see that the net force on either nucleus points toward the middle. All right, if you look at this and say, what does it add up to? It adds up to a force of 3 nanonewtons pointing toward the middle. 4 and 1 add up to 3. Now I'm looking at diagram B. I'd like it if you would analyze this before I calculate it, but I'll start you off by saying, here's an attractive force. The positive is attracted to the negative. You can calculate the magnitude of that force. This plus 2 is also attracted to the electron. It's a greater distance, but it's a larger charge, so we should calculate what is that force of attraction. In addition to the forces of attraction, we have forces of repulsion. The force of repulsion between the nuclei will push to the left for this one, but will push to the right for this one. So here we have an example here of two forces pushing in the same direction. Here we have, on the left, we have forces pushing in opposite directions. Try to calculate those forces before I show you the answer. For this first force here, I have F equals 4, Q1 is plus 1, Q2 is minus 1, so 1 times 1. Distance is 1. You should see this is the same force we had before. This blue attractive force is 4 nanonewtons. For this second nucleus, then we have force is K, which is 4, Q1, which is 2, Q2 is the electron, it's 1, it's far away. It's 1, 2, 3 units away, so distance is 3, square it. This gives you a force of 8 over 9 nanonewtons, so less than 1, 8/9. Distance has a big effect on the strength of the force. Now the repulsive forces. They'll be equal and opposite. So if I've calculated it once, I calculate it for both. The repulsive forces I'm writing in red. I have Q1 and Q2. So it's 4 is the K, Q1 is a 2, Q2 is a 1. Distance is 1 plus 1 equal to 2. Square it. I've got 8 on the top and 4 on the bottom. I have a repulsive force of 2 nanonewtons. A repulsive force of 2 nanonewtons. So in this case, you can see the net force is the sum of the two. In this case, pretty big force, 6 nanonewtons pushing this one to the right. This, they're fighting each other. It's 10/9 pushing to the left is the net force for this second particle here. Here is the second scenario, diagram B in interactive physics. You can see these two came together, forces of attraction dominate. But this ion here, this nucleus here, the forces of repulsion dominate as predicted in our analysis. So it gets pushed off the screen to the left. I'm jumping ahead to diagram D. Here you can see two nuclei. Here's one, there's two. So they repel each other. Here are 2 electrons now. They will attract the nuclei. You can see I've got some nice geometry going on here. If I sketch this little dashed line here, you should see a 30, 60, 90 right triangle. And it turns out that these vectors, these arrows that I'm drawing, geometry is essential here. Alright, so we can try to calculate the force of attraction between this proton, this nucleus, and the electron. This should be easy to do using our familiar formula. So F equals K, which is 4, Q1, which is plus 1, Q2, which is minus 1. Distance is 2, so square it. 2 squared, and we get a force of 1 nanonewton in this direction. You should see by symmetry that it would be the same in this direction. The distances are the same, the charges are the same, and you should see that we've also got that here. So we have 4 forces for the price of 1 calculation. These 2 vectors here will add together, but they don't line up. These vectors can be added together geometrically. The vertical components will cancel out. So this upward pull will be canceled by the downward pull from this other electron. So it's only the pull toward the middle that will add together. So it turns out that when you add up it's called the x component, these two will add up to square root of 3. Similarly, this one will have an attractive force straight down the middle here, square root of 3 nanonewtons. So the 2 nuclei are pulled together. They also have a repulsive force, which we can calculate with a little geometry. If you understand the nature of a 30, 60, 90, if this distance is 2, this distance is 1, this distance is square root of 3. So the distance in my diagram is 2 square roots of 3, the distance between the 2 nuclei. So I can calculate the force of repulsion. Force equals K, Q1, Q2 over 2 square roots of 3. That's the distance, square it. And we get 4 on the top and 12 on the bottom, so that's 1/3 is the force of repulsion. 1/3 equal on both sides. Alright, so there's my diagram. You can see here, I think, that the force of attraction, the green force of attraction here, outweighs the force of repulsion. So these nuclei should be drawn together. It is a bonding arrangement. Here's the last scenario that we've modeled mathematically. Nothing's anchored here. And look at that. A nice bond is formed, very symmetric. Let's see what happens if I anchor the electrons. Okay, the electrons can't move now. Let's see what happens. Attraction, repulsion, attraction, repulsion. This is actually a more realistic view of a bond than the static picture we had before. The nuclei will tend to vibrate. So it's a kind of a stretchy bond, a wiggly bond, not a solid, rock-solid bond. But it's always the forces of attraction and repulsion that rule the physics of the atom that determine whether a bond will or will not form. I've turned on vector display, so the arrows we were drawing on paper are now visible on this interactive physics screen. It's misdisplaying this vector here, the repulsive force vector. That should be 1/3 of a newton. Now I'm letting it run, and you'll see that the vectors change because the distances change. And as the distance grows shorter, these forces grow larger. The repulsive vector changes the most because the approach of the 2 nuclei They get very close to each other here in the middle. So when they get close, then repulsive forces dominate. Now attractive forces dominate, drawing them together. Repulsive forces dominate, pushing them apart. This is the physics of a covalent bond. It's beautiful.